But for the next 90 minutes or so, and then we'll try to make sure we have time to go and get more beers together, I wanted to talk a bit about why I'm so excited about C++. And yes, that's pretty much every year. But it really is, I do feel different about this year. I did not know at the beginning of the year what was going to happen in the committee at the Tokyo meetings for safety, at the June meeting in St. Louis for reflection. And both of these things are things that have been coming together and being worked on for a decade or more. But to see them start landing in the standard and other cool features in draft C++26, that is really making me aware that this is a pivotal time for C++, and it's the kind of thing that gives you tingles. So let me explain why I feel that way. Maybe by the time I'm done, I will have convinced a few of you that the C++26 and the 29 standard to complete 26 really feels like it's a treasure chest that's being put together. And I know what some of you are thinking. No, that's not a mimic. Okay, we just identified all the D&D people in the room. But there are other cool features, don't get me wrong. The committee has been very busy. Thank you to all the committee members who aren't here and those who are here in the room. Some of this is your fault, I mean your work. And we have great stuff stood execution, which has amazed me personally. I'll just say in a couple of sentences why. This idea of executors, the idea of talking about where a locus of execution, where something should continue working next, a task, a continuation, that's something we've been working on for a decade now. I've been teaching concurrency a lot for the last 20 years. And one of the fundamental things I teach is that concurrency and parallelism are different things. Concurrency is about letting independent, different units of work, different tasks run at their own speed and not interfere and communicate by messages, that kind of thing. So different tasks run independently. Parallelism is how do I compute one thing faster using more cores, using more hardware to get get one answer faster. I am pretty shocked that we have a stood execution where the concurrency folks are telling me, and I'm not the expert, so I'm learning now like you are about this, that the concurrency folks are telling me that this is the greatest API we have yet on top of coroutines, which is concurrency, all about asynchrony and hiding latency and that kind of thing. Meanwhile, the NVIDIA folks are saying, yeah, we run this and it competes well with CUDA on at least the workloads they've tried. That's state-of-the-art, best-in-class, world-class parallelism. So I'm pretty interested in looking more into that because I want to see how they did that to satisfy those two very different domains in a single thing. But this talk is not about stood execution. I just had to say that because I'm very impressed to hear those two camps being both thrilled about stood execution. We're working on contracts. We're going to have lots of wonderful discussions about that again next week in Poland, in Wrocław. But I want to focus specifically on these two things, the type and memory safety improvements where our target is not perfection, but parity with other languages. We're all imperfect, but we are more imperfect than others, and we want to even that out. And then reflection and code generation. And when I say reflection, I always mean code generation too, but because sometimes people think of reflection as read-only, I try to emphasize it, so I'll try to keep saying and generation. It is part of the 30-year tide in C++ toward more and better compile-time programming. I'm not going to ask for a show of hands because I hope every single one of you was in the room for Hannah's talk this morning. And if the end of that talk didn't tell you everything you needed to know in that list about more and more compile-time programming, we're not stopping anytime soon. The usual joke is that compile-time programming will know we're done, that we put the entire language and library available at compile-time when we have stood thread at compile-time. Yeah, you laugh, but you didn't laugh when Hannah showed coroutines at compile-time, which is a hair's breadth away from that. Like, that is a hair's breadth away. So if you're paying attention to our last slide, you will be less surprised if we see Stood threads running at compile time. Oh my goodness, what are we doing? But it's going to change the way we program for the better, the way that we write not just our code, but our tools. And that's what I want to delve into, these two areas of safety and reflection. So we'll start with reflection, and I'll give an overview. Then we'll go to safety, and I'll give an overview about why each is making good progress right now in 2024, and why I think 2024 has been a pivotal year for these things to start entering the standard. In the case of reflection, being at least design approved in the evolution groups. It's not in the draft standard yet, but it seems to be on track, fingers crossed, for having the first parts in C++ 26. And then I want to go back to both of them again, number one and number two, in the context of simplicity. Simplicity for the code that we write that comes out of our fingertips. Simplicity in our tool chains and our build environments. And how both of those, I think, are very promising to be a step change, improvement in both of those things. Now, normally I try very hard to have one talk, one topic. So you might say, reflection, safety, aren't those very different things? Well, I already showed they're going to lead to, they overlap to simplicity, and they're going to change the way we write code and think about it. But also the timing that both of these are starting to come, serious improvements, it looks like in 26, and they are technically related, down arrow, UB. Hold that thought, and we'll come back to that a few slides from now. So let's start with reflection. What is reflection? It's literally meta programming. The program can look at itself. It's like you when you look in a mirror. And why do you want generation, not just read-only reflection? Why do you also want to generate source code then based on that? Same reason you walk and well, I hope that you look in the mirror in the morning. And then you don't just look, but you want to do something about what you see, you know, put on some concealer, comb your hair. Like hopefully you want to do something based on what you read, not just look at it and say, I'm pretty, and walk away. True as that is of everyone in this room, you also want to even do more. The big difference between reflection as it's being proposed and designed for C++ and in other popular languages that you may be familiar with is for C++, unlike, say, Java and .NET, it is purely static compile time reflection. Zero runtime impact, unless, of course, you ask for it. Like if you want to keep something you computed away at runtime, just store it. You can do that. But you opt in. This is C++. We try very hard as well as we can to follow Bjarne's principle, don't pay for what you don't use. If you want to use it, then you can pay for it. This is the, I almost want to say culmination, but we'll always discover more steps, but it's the culmination for now of what I see as C++'s 30-year arc of, among other improvements, one thing that we see as a tide is more and more support and direct support for actually computing things at compile time. And as Lao Tzu pointed out, one way to really appreciate that is to go back and look at the humble beginnings. So let's do that and look back into the mists of the past in 1994. What does TC stand for? This is a quiz. Now, I'm putting it as a shorthand, so I'm asking you to read my mind. It's not like it's an industry term or anything. But in this case, it stands for Turing Complete. We discovered in the early 1990s, I think a couple of years before this, but Erwin Unruh really rubbed the committee's noses in it when he came up with this beautiful program that doesn't compile. Now, today it doesn't compile, in part because syntax changed, like main now has to have a return type. But even at the time, this program did not compile on C++ compilers, and that was super great and made it super famous because of the way it did not compile. In the original Metaware compilers, these were the error messages that you got, where we were abusing the template type system to compute primes. We do this every day of the week now. This was magic in 1994 because Bjarne, bless his soul, wanted to have, you know how he'll always say, rightly, he wants to design a feature that does more than what he can imagine it's used for. He wants general features. Good idea, good design point. Yeah, so Elvin came around and said, do you know you made it Turing complete? And Bjarne says, what? And Bjarne said, yeah, look what I can do. And then, of course, since then, the floodgates were opened. It was an indoor sport to figure out how you can do more and more template meta programming. And Andre is much to blame for this. So that was 1994. By 2001, Andre, with his cheekily named Modern C++ book, because the vanguard of C++ then was template meta programming, wrote a whole book about it. This is one of the most influential books in C++'s history after Bjarne's. And it's still in print. It still has techniques that are useful today. But it really showed how far you could go with abusing, for fun and profit, a template type system that was never designed to compute anything. It was for type safety. For typing. It wasn't designed to be a functional language that you could use to compute things. But if you have specialization and enums, you can use it as that, it turns out. And spin A is always good. What is better than indirectly expressing your program? Directly expressing it. So over these years, from 1994 to C++11, it had become clear that C++ programmers, darn it, they wanted to write compile-time code. They were going to write it no matter how hard it was. Maybe we should support that more. And so Bjarne and Gaby Dos Reis were the primary authors, and with the help of many, many committee members, in C++11, we got constexpr. And this was a game changer. Now, you would be forgiven if at the time you missed it. If you were in 2010 to 2011 and you saw constexpr and you thought, yeah, that's just really a small feature, that was entirely forgivable, entirely understandable, because all you could do was write a constexpr function with one statement in it, one return statement. That's it. So, of course, the ternary operator got very popular, but it's just one statement. What could it be? If we get the basics of reflection in C++26, as it currently looks like we will, and I'll describe that in a moment, we will be in a very similar state. But see it for what it is, a game changer, because that's only the first step. For the next standard cycles, we kept adding more and more. Oh, you want loops? You want conditionals? How about lambdas? How about if constexpr? How about new and delete? Why not allocate memory at compile time? Think about it. Well, you already have because of Hannah's keynote. And more support for allocators, non-literal parameters, and the end of Hannah's talk showed you just how much more there is on the horizon. Essentially, in a nutshell, pretty much, not everything, but pretty much most of C++'s language and library are now available in constexpr code. Now, how many of you have done work on GPUs? Yeah, especially these days, right? Like all the cool kids' workloads run on GPUs now, right? So at first, we had just shaders. How many of you remember the days where you would try to do compute using just shaders? Okay, oh, wow, wait a minute. There were more hands just went up for that than for, never mind. I guess for the first question, you're like, oh, of course. Like, well, I'm not going to raise my hand. Of course everybody does GPUs now. I'm not going to bother with that stupid question. Oh, shaders? I did that. Okay, but the idea of shaders is that the GPUs, at least at the time, and now things can be more complicated, you have more options, but it was basically a streaming memory model. So in the CPU world, we were all about how big is your cache and how deep is your cache, and GPUs are like, cache? Who needs cache? Memory is fast. If all you're doing is you already know the memory access patterns, so the hardware can just shove all the memory past you because it already knows in advance what order things are going to be accessed, all that memory is just flowing past you, so a streaming memory model. And a shader is, wouldn't it be convenient if you could throw a couple of instructions at that data as it went by, and maybe, to maybe modify the data? 16 instructions should be enough for anyone, right? And again, it turns out that people use it. So that became 32. It became a K of instructions. It became N instructions because, oh, you want loops? Oh, well, okay, we can give you loops. Oh, lambdas, templates, you want static assert? You C++ people are greedy. Do you want concepts, ranges, new and delete? So all of these things, and if you've been paying attention, here's the previous slide, and these are the two going back and forth. There is a lot of similarity between these evolutions. And there's a highlight of what's the same. So pause to consider what this means. As we're developing a language for, hey, in C++, we would like a language to do things at compile time. We didn't invent some new divergent language or syntax. We abused templates at first, but then when we got serious about it, we said, well, I like C++. I'm already writing C++ in the source file. Wouldn't it be nice if I could run it at compile time? Oh, my C++ program is doing work on a GPU. What language should that be in? Well, it could be in some other language or API, but wouldn't it be nice if I could run my C++ code on the GPU? So that's the evolution that we've gone through stepwise. So we didn't get everything in the first release, and that's why I want to temper your expectations. The best case is that we get P2996 in C++26, fingers crossed. But that will be just the first step of a decade-long evolution. And I say decade-long not because it will necessarily take that long to standardize everything. It's going to take us that long to learn it once we get the tools, once they're built out, to learn what is possible in this new world, once we have reflection and generation in a way that no other major language has it, statically at compile time, in a flexible way. So I'm going to talk quite a bit about P2996 examples, but there's already more proposals about introspecting more things and then doing actual generations. So I'll do a dotted line where we actually go into generating new source code, new types, new functions. And so again, this is a stepwise thing. We're not going to get everything in C++26. But boy, if we get even that first step, it's going to change the world. Let's take a look. So here's an example, and I asked the reflection paper authors for examples, and here's one of many from the paper. You can read the paper and find many more. Most of us understand a command line options parser. So we've probably all used several. We've probably built and designed several, because like we all do, right? I did my own for CPP front, rather, because I just wanted to do my own instead of have a dependency on a third-party library. And it worked the way I wanted. But notice that when I say myopt equals parse options myopt here, this looks like a normal function call with an explicit template argument. Yeah, we could write that today. But there's something new going on, because yes, we're just passing it a struct we wrote, and we're calling this function. That's fine. So what's the magic? The magic is that if you go into the function, again, it starts, if you don't really look too closely, it looks like another template function. Parse options that's parameterized on type name opts. Takes the actual arguments, the runtime arguments, as ordinary parameters, a span of string views, okay. But then it starts doing something that actually is new. So this syntax may change because the proposal is still being reviewed and it's not merged into C++26 yet. But I can do a compile time for loop over the non-static data members of, so the member variables, of reflect opts. So think what this means. It's saying, look at the type, actually do a for each over the data members of the type. And for each data member, I can see the type and its name and maybe offset or whatever it is I want to compute about it. And then I'm going to just do my usual things, call std ranges and all the great things. And I'm just going to say, hey, is this name one of the command line arguments the user actually gave me at runtime right now? But notice I'm building this loop at compile time, saying at runtime, is this one of these? And if so, I'll go process it. If it's missing a value, I'll do my usual error handling. And as I'm doing this, this template type, is more than it ever was before. Because we're used to type parameters. We've been using those for 25, 30 years. But now the structure of the type is the input. Do you see what I mean? I want to tell parse options to parse a string file name and an int count, but instead of passing those as parameters or as a vector of parameters, a runtime data structure, I'm just giving it the struct and say, just look at the way the struct is. One data member is one kind of command line argument. So I'm actually using the type itself as a function input in a new way, right? So that's an important observation to make. And it's pretty subtle because the first two lines look pretty much the same, but that's what I'm doing. Then there's the expansion statement, the reflection expression, and I've got a bunch of std meta functions that are being proposed that let me look at reflections and compute things about them. And then here's the other half of it, is then I can do things like splices. So I can try to read, if I find that, okay, the user said, here's the command line argument, or here's the command line flag, I look it up in the struct, and sure enough, there's a member with that name. So okay, that's the one that the user is trying to specify on the command line. What's the type? Say it's std string. I'm now going to try to stream it as opt.name, as that type. And that's type safe now. And it's going to do a stream into a string and do a string conversion and all the usual things you would do. But I'm doing all this selection at compile time to build the program that's going to run at runtime. And once I do this, and you can actually run this on Compiler Explorer today. So the code I just showed, you can, I think I showed, did I give the link here? Let me just make sure if I gave the link. Okay, I think the link comes later, but you can take this code, cut and paste it. And when you do, say you do --count42 -- file name Scott Meyer's effective modern C++ PDF, because of course you should all be reading that. And that it just prints out that, okay, I built an option struct where the file is the string, Scott Meyer's emcpp.pdf, and count is the int 42. And if I had done something that was incorrectly typed, now this is kind of dynamic typing, if what the user had written on the command line was not correctly typed, like they say count Scott Meyer's effective modern C++. Well, count what? The pages, the words? Like what? That's a string, that's not an integer. Then you can get the error message, no, I couldn't stream that string, that did not contain an integer because it's trying to convert it to an integer. So you get type safety. That's a very tiny nutshell example. There's actually a second command line parsing example that's even more interesting, but I picked this one because it fits on just 2 or 3 slides and it makes it easier to explain. But you can get really fancy real fast. Look at command line arguments 2 in the paper. If that interested you at all, you'll find even more. So where is this right now? It has been design approved by the language evolution subgroup for C++26. It's not yet part of the draft standard because the library evolution subgroup still has to approve the library part of the design, and then it still has to go through the specification wording review and then go to the vote to say, yes, let's merge this into the draft. But it's on track for that. We've got several papers on reflection and refining this model further that we're going to be busily talking about in Wrocław next week. But so far, so good. And the implementations, there are 2 current implementations of P2996 and its active sister proposals. One is by EDG by David van de Voorde of EDG fame, and it's no surprise in the EDG compiler. And by Dan Katz of Bloomberg, he did one in the Clang compiler. And they both have pretty much P2996. Some of them go further, like David's goes further and does the example we just saw that does or an example we're about to see next that does actual generation. and it has some of the later proposals already as well. And there were previous proposals as well. So all of this is built on other work, especially Andrew Sutton's Lock3 implementation. That's one that's been going since about 2017. And that was funded from and designed for CPP2 work before CPP Front existed. So it was one of the early prototypes for that. And I'm thrilled to see that now feeding into standardization for ISO C++. That's the whole point, is we want to deliver reflection to millions of developers. So let's talk a little bit about safety. And I use this graphic now as we switch gears for a second. I use this graphic deliberately because we absolutely need to talk about memory safety. However, please do not lose sight of the fact that it is one of a dozen or more different attack vectors. And that if we could wave a magic wand and make all the C code and even the C++ code in the world memory safe overnight, and in Java and C# as well, we would not be solving 70% of the memory safety we would be solving 70% maybe of the memory safety problems, but not of all the vulnerabilities. We'd be doing nothing about supply chain attacks, impersonation, data hijacking, not validating your inputs, SQL injection, and all the others that we still have to deal with. So we have a lot of work to do as an industry. And a lot of it falls on C++ because we're so fundamental as a building block. It's such a foundational technology that the world is built on. But we need to clean up all software. But let's here just talk about memory safety, because that's something that's important and current. So just to define some terms, each of these terms has several overloaded meanings. So I'm going to try to be very specific. When I say security, software security, I mean that your software can't be broken into. The software can protect its assets. And this is what you want for your power grids, for your hospitals, banks, personal data, and those kinds of things. But we also care about software safety. You'll sometimes hear life safety and things like that, where we want our self-driving cars, our autonomous vehicles, and autonomous weapons to do no unintended harm. That's a very precise description, by the way. And then programming language safety feeds into both of those. If our foundational programming languages are memory safe and the more correct those programs are, the more our software will be secure, the more our software will be safe as well for protecting its assets, for life safety. And we're going to talk about more on this in section 3. So what's the actual problem? You can write bugs, including safety bugs, in any language, even without using the unsafe keyword. Java and C#, you can read uninitialized variables. How many of you know that in Java and C#, in purely safe code, without using unsafe, you can read uninitialized variables? Yeah, just do a virtual call in a constructor, because virtual calls and constructors are deep, which means they will access unconstructed derived classes. They will invoke the derived versions, and those members haven't been constructed yet. So that's what we teach. So I'm not saying this to throw mud at C# and Java. They're great languages. I'm just pointing out that safety is a spectrum. It's not binary. All languages have bugs. What we want is to reach parity with other languages, because yes, those C# and Java have those problems, but we still consider them memory safe languages because they're good enough, right? They are sufficiently safe that they catch those categories of errors, those classes of mistakes, some of which are not caught in C++, and so we want to level up our game in C++ to have parity. Because if, just as a data point, all this discussion we've been having for the last 3 years, especially about memory safety in C and C++, well, first of all, it's mostly C, but also, yes, some C++. We would not be having this discussion if memory safety errors were 90% fewer than they are. even if they were non-zero, we are only having this discussion because it happens so often and so easily, even when we're trying to write good code. So what are the 4 differences, the main differences between, say, C++'s guarantees and, say, C#'s guarantees? Bound safety, type safety, initialization safety, and lifetime safety. Those are also the 4 most severe vulnerability and weakness categories. They're the 4 things that the memory-safe languages, though not perfect, do way better at. And so those are the things that we want to improve. So what have we been doing? Well, we've already been making some progress in building safer libraries, such as having a stood span since C++20 to replace pointer arithmetic with basically a fat pointer that knows its bounds, but it's actually a better abstraction. It's an abstraction of a contiguous sequence of things. We are now removing safety-related undefined behavior. More on that in just a moment. We're working on static safety profiles. We're going to be talking a lot about that next week at the standards meeting across the border. And we're looking relatedly at adding dynamic safety checks for things like subscripts and dereferences, the key things, the low-hanging fruit. And then there's other stuff where implementations are also upping their game because we gave implementations latitude to do better, and they haven't in the past. They are now getting serious. GCC, Microsoft, so Apple's been doing great work. Louis, are you in the room? No. Well, we have lots of folks doing great work, even outside the standard, and it's great to see all of this improving in so many ways. Because we do not want to take away sharp knives from C++ developers. We use C++ because we want access to the sharp knives, right? This is the language that gives you control over space and time. It gives you control over space, object layout, where objects go, right? So you can really control space. It gives you control over time so that you can control the performance overheads of things and not pay for things that you don't use, right? So we want those controls. But right now, all the sharp edges are just littered around the floor, and you have to watch where you step. So today, the model is watch out and just don't use the wrong thing because all those sharp edges are exposed by default. Imagine the same kitchen, but all we do is put the knives in the drawers. They're still there. Nobody's taking away your knife, but just open the door and then disable a safety profile. They say, no, I really want to disable subscript checking in this hot loop so it vectorizes. And I know I already checked the subscript. You just can't prove it. Trust me. Cool. We just don't want that to be the default with the knives lying around the floor. It's mostly a question of organization. So I would like to see if we can change the watch out model to the opt out model. It's kinder and gentler. And one way to look at this is to change from our current view that we have performance and control. Safety is always available. You can write safe code in C++. It's just not the default, and you have to be careful. To change it to safety by default, performance and control always available. That's the mental shift that we're doing our best right now to navigate. So safety profiles are progressing in WG21. Each profile is a set of rules enforced at compile time. Typically at compile time, some checks need to be runtime, such as subscripts, but most of them are at compile time. That guarantees that your code is free of a certain class of defects and that you can opt into and opt out of. Most of these rules are ones we already know, such as, the C++ core guidelines has thousands of rules. That's way too many to know. But right at the end, it's got like 24, just 24, small number of safety rules. And what are they bundled into? Type, bounds, initialization, lifetime, those 4 buckets. Rules like those, and we just want to shift left them to compile time, so that they run in the compiler. This is a big deal because today, even if you run a static analysis tool, never mind that it gives you all these 1,000 warnings and we want to specify, no, here are the ones we want to get serious about. But people don't always run those. They run them later. They run them post-check-in. What you really want is these rules to run by default, have them be efficient enough and on by default to run at compile time before you, the developer, before I, the developer, get to check in the code. There is huge value in that. Here's a snapshot of the cover of the book Effective C, written by Robert Secord. There's a picture of Robert perusing his book. And Robert's background was from places like MITRE and CERT. So he was interested in cybersecurity and memory safety as well as C. He's now the convener, the chair of the C Standards Committee. And there's all sorts of good quotes on the praise page, including that, hey, we love C because we want to use all the available tools it presents and also avoid undefined behavior. So we want to avoid undefined behavior in the C programs we write. So a lot of Robert's book is about avoiding UB. There's also this other juicy quote in the box at the bottom that I'm about to show you that crept past the editors. This is why you should program in C, because other languages don't open portals to hell. On the cover, who's that? Yes, the old dark one. Is that the right term? Say again? So Cthulhu, the idea of like this ancient demon or whatever, of undefined behavior, because when you have undefined behavior, but he's got this cute sidekick on his shoulder, so the robot's cute, so that makes it okay, right? The idea of we use C because of undefined behavior. So Mikhail Zalewski was being facetious there, but he also was making a point because a lot of the things we want to be able to do in C and also in C++ rely on the fact that we get to not have all the guardrails all the time. So this is both a blessing, though, and a curse. Wouldn't it be nice if we could put more of those knives into drawers so that we still have the language we love with all the sharpness when we want it, but not always opening portals to hell accidentally on every 10 lines? That's probably a better story. So undefined behavior today can mean, demons can fly out your nose, anything can happen. In reality, it means information disclosure, time travel optimizations, things like that. What we did in our Tokyo meeting in March was we adopted, and thanks to Thomas Köppe and many who helped him with that proposal, we've now adopted for the first time in a couple of decades a new form of behavior. We had like well-defined, implementation defined, undefined. That was the fun one we were just talking about. We added a new one, erroneous behavior. So we formally made a word of power in the standard that says, we now have a word for that thing you wrote that, yes, it's partly our fault because we said that's legal code, but it's wrong. It's just wrong. And what we did is by identifying that we now have a tool that we can use to point at code. Notice I've been pointing at an empty set of seats here at the front so as not to put anybody on the spot. But we can say when you write this code, it is wrong, but it is no longer undefined. You cannot get time travel optimizations. You cannot get undefined behavior, nasal demons, information disclosure, leaked secrets. It is now going to be well-defined, but still considered wrong so that your tools can tell you that you did something wrong. It's still you have a bug, you need to fix it, but it's not a portal to hell. It's not going to summon Cthulhu. And that's a general tool, but the very first thing we applied it to was reading uninitialized local variables. I don't know if you noticed this, but as of March, so as of like 7 months ago, whatever, 8 months ago, reading uninitialized local variables in draft C++ 26 is no longer undefined behavior. This is huge. It is only the first step in applying erroneous behavior, but let me describe why this is huge. It is huge quantitatively, and it is huge qualitatively. It is huge quantitatively because we can automatically eliminate some fraction. It's a minority of bugs. Like most UB is not uninitialized local variables, but a noticeable minority, a percentage, is. And we can now get rid of that just by recompiling, and that leads into the qualitatively. We can deliver this advantage to existing code just by recompiling it in C++26 mode. Think about what that means. How often do you get the holy grail of adoptability? The holy grail adoptability story is, I didn't have to change my existing code at all. I recompile it and it gets better. We did that in C++11 with move semantics. So how many of you had the beautiful experience when you got a shiny new C++11 compiler that knew about move semantics and knew when to automatically do moves in at least some of the places without you having to say it in your code? How many of you had the experience that when you took your existing code, recompiled it with the C++11 compiler, and you noticed it got faster? Wasn't that a beautiful day? We're doing it again for safety. And in case you think I'm making too much of a deal about, oh, I'd initialize local variables. Okay, so they fixed one thing. But remember, we just adopted a general tool. This is the first place we're applying it to. There is a paper, I wrote it, that we're going to be talking about next week, which is about removing a strategy for removing all safety-related undefined behavior from C++ by default. You can still opt into it when you want, when you need sharp tools, and especially when you know that using it is not likely to be UB because you know more about your program. But this shows the committee, this gives me hope, because it shows to me the committee is serious not only about making a real tangible improvement, but dealing with adoptability, doing it in a not ivory tower theoretical way, but in a practical, easy to adopt way that takes into account the existing billions and billions of lines of code. That's really important. Just to show you what this does, consider this function where I have a main line that calls f1, then f2. f1 has a local array that contains a secret. Then it returns. Then we call f2, which lays down a character array on the stack, or could be anything else, but let's just do a character array. It's easiest to show the problem, and doesn't initialize it. So what's there? Could be anything. It's undefined behavior. Most likely, though, it's whatever bits were there before, which is whatever the previous function stack frame left lying there before it returned. So if you print the local variable a in f2, you will very likely print the word secret. And in C++26, you will do something else. We don't say what it will be. We say it will be well defined. If you don't initialize that, the compiler will initialize it with magic values and be able to tell that you did something wrong. It will not be UB. And there are tools you can use today, even before you get a C++26 compiler, in GCC and Clang and MSVC to do this. So here's what it looks like. I have f2, and I print my local array that I did not initialize, and look, there it is. On all three compilers, it actually prints the secret. And when I use today's switches, it's fixed on all these compilers, and the only difference coming in C++26 is that you won't need those switches anymore. That will be the default for all C++ code. So some quick question and answer. Everybody asks, why don't you just jam in zeros? Why don't you just automatically zero initialize? After all, other languages do that. And that would have been a fine thing to do if you had a time machine, right? If you could have done it at the beginning before there was code written, before C++ code was being written. The problem with doing that now is the person who wrote that existing code that has an uninitialized variable, you don't know, you can't read their minds. You don't know what they meant. Zero might not be a valid value for that variable. You don't know if it's even program meaningful. So there are real problems with doing that. And worse than that, it actively hides real problems, because if you just start jamming in zeros, then if you're running later an undefined behavior sanitizer, which looks for uninitialized values. If it's relying on the values that are sitting there, it sees 0, it's easy to fool. It may think, oh yeah, it's initialized. But it wasn't really initialized by the programmer. The compiler just jammed in a 0 that might not even be program meaningful, and so it masks the actual bug from that kind of sanitizer. So those are some reasons why not just to jam in zeros. Next question is, can I open that drawer? Can I have that knife, please? Because I really don't want to initialize this right now. Sure, there's an attribute called indeterminate. And if you're like me, the first 6 times you will write uninitialized, and then you will learn that's not what the word is. It's indeterminate, and then you'll get on with your life. Why didn't C++ always do this? How many of you noticed that when I was describing this beautiful world of rainbows and unicorns and how the UB goes away, how many of you thought, but the compiler's is making us do more work? Isn't that going to slow down my program? Okay, a few hands are like, yeah, I was kind of thinking that. So technically, the code will be slower. Now that I've scared you, think about what that means. It is very often going to be unnoticeable. But if it ever is noticeable, that's why you have the opt-out if you really, really meant it. Because we now are going to be doing memory writes. Even if you didn't ask for them, they may be to like hex CD, 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 or something like that, that a sanitizer can tell means wasn't initialized, but you will be doing writes. Why didn't we always do this? Because especially for big arrays on the stack and for big objects, which is usually big because they have big array members on the stack, that was in the past and still is a significant performance penalty. And so that's why for large objects and for arrays, especially, there was motivation not to do that. Now, times have changed. Safety is more important and certain things are more efficient, but that was a historical reason. But we'll talk in a bit about how we can do even better. So if I were to tell you that C++ could evolve to eliminate most safety-related undefined behavior by default, how many of you would believe me uncritically? It's like, do I work? Yeah, so like this isn't a cult. We don't believe uncritically, right? So there are a few hands. But most of you are like, show me, tell me more. Where's the data, right? Exactly. We already do in large swaths of the language. Remember, we were just been talking about 2 things: compile-time programming, const eval, reflection generation. And we're talking about safety, profiles, checks, guarantees. Both of these are related in that they're about having much less undefined behavior. Now, that's obviously important for safety to have less undefined behavior, right? That part of the Venn diagram is obvious. This part may not be, but C++ already has huge amounts of code where there is no language undefined behavior. And what's the keyword? Const expr. Why? Because you're not allowed UB in that const expr. Right. So all that const expr code that y'all have been writing and writing more of and more of, did you notice it has no UB? Signed overflow, even signed overflow, I mean, that's the poster child of the check that no language turns on by default, not even C# because it's so expensive. But even signed overflow, sum pointer arithmetic, division by 0, and many of these things are safety related. So here's a Godbolt example where I have a const expr function, f, that computes a factorial, because that's what we always do in our const expr functions. And notice there isn't a red squiggle directly. There is a red squiggle on the star equals, but that's not the root cause. That function is fine. I could call f of 1, f of 2. It's perfectly fine at compile time. But notice when I force constant evaluation, so I force this to run at compile time by having a const expr int x initialized to f of 13. It turns out factorial of 13 is kind of too big for an int. And so every compiler, GCC, Clang, MSVC, they all tell us about it. And notice they don't say you can't call, that F is bad. You can call F5, no problem. It's the call to F13 that gets flagged. Because one of the things const expert code does is it basically runs a C++ interpreter, essentially, inside a C++ compiler, and so it can tell. But a lot of people don't realize this. We have quietly been adding a huge UB-free zone inside C++, and no one almost noticed that we have done that. So let's see how both of these things, reflection and safety, are things we can build on further to make our code simpler and make our tools simpler. Every time you see a new proposal for our already complex language, people will think, my goodness, C++ is already so complicated. It's the biggest language I know. I mean, it's a badge of honor, right? It's like, I know this language, but it's already so complicated, and you want to add another feature? And as Bjarne likes to point out, there is a bit of a hypocrisy or duality there, because people will simultaneously say, C++ is too complex, we're adding too much, and then say, I would like this feature added, please. We all do that. We all do that. But it's true, we can't just keep adding features. Any mature language comes and hits this. The C# designers, the Python designers, I hear this from all of them. So how do we characterize improvements that are beneficial? Well, and especially improvements that can simplify the language, simplify code. And the thing to look for, I will argue strongly for, the thing to look for is adding an abstraction that lets the programmer express directly what they had to express indirectly before. So you add a language feature like the range for loop. Yeah, you could write a range for yourself for int I equals 0, I plus, or say, let's start with, use iterators and go dot begin and doesn't equal dot end plus plus I. You can do that yourself. But there's nothing declarative in that loop, and it hinders some kinds of optimizations and analysis because you can't, without reading the body of the loop, know that, oh, it really does iterate once over each element. It doesn't skip elements, things like that. The range for loop made the language a little bigger because we added a new feature to the language, but it made C++ code smaller and simpler. How many of you have used range for 3 times a day and twice on Sundays? Right? We're not going to go back to just having to do everything by hand. So when you see examples like that, where you see, especially people are already writing code that's a pattern, look for how can language support make that code simpler. That's the special sauce. That's the magic sauce for adding to a language in a way that makes the code simpler. And it is possible. I firmly believe it is possible to simplify a language when you think of it not from the point of view of the number of pages of the language spec, but of the point of view of the user, the code author, simplifying the code that we write. And we'll talk about toolability as well. A key shorthand for this I use is elevating coding patterns into declaring what I want to do, not how I want to do it. If I can say what I want, visit each element of this range, not how, take this iterator, increment it, test against end, you're going to be better off. So let's see how we can apply that principle first to reflection as we build on that, and then on safety. So 7 years ago, I wrote paper P707, the first revision about metaclass functions. And I have a new revision in the mailing for next week, but it is now something like 6 pages, where it used to be like 100 pages. And the reason is because the first version had to say, basically, most of the page count was, please give us reflection. Here's why we need reflection, and here's all the things we can do if we have reflection. Now that there's a whole reflection proposal being adopted, I can just say, hey, with that thing over there, let's build this little layer on top of it. So that's what the paper has turned into. So I'm profoundly gratified to see, and so I've been watching over the last 7 years as Metaclasses have been getting closer and closer and into the standard through reflection and being a platform to build on. At the very first meeting, I proposed it. As I said there in the middle, I got up in the session. There had just been a presentation by the then reflection designers, and I was next. And the very first thing I said was something like, "Hi, I'm Herb, and I'm their customer." Because it's just purely about building on top of reflection and saying, what can we now do with it? So I'm trying to be very crisp on what's actually going on its way into the standard, so other people's proposals as well, what the committee as a whole is approving, excuse me. And what I'm proposing on top of that, I'm trying to keep those apart. So this example is possible with P2996. This code has been design approved by the Evolution Working Group. I propose that we add, this is my proposal, can we please have this as syntactic sugar for that? That's all. Once we have suitable reflection and generation, the Metaclass proposal really comes down to a syntactic sugar transform, but just like lambda functions, an important syntactic sugar. So here's a quick refresher example of the motivation behind Metaclasses. Today, I can write an abstract interface, an abstract base class with pure virtual functions, all public, not copyable, got a pure virtual destructor, blah, 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 all those things. I can write that. Notice I wrote default in the right places, delete in the right places, public virtual equals 0 in the right places. And I'd like to just say, hey, you know what? I'm not writing just any class. Because you see, when I write class IFU here, I'm just saying I'm writing a class, and then I have to say how. If I can say what, I'm not just writing any class, I'm writing an interface. And we'll define that to mean has only public pure virtual functions, no member data, has a default constructor, a public pure virtual destructor, is not copyable. Now I've declared my intent. I get the right defaults, I get the right generated functions, so I never need equals delete to opt out of a generated function that I didn't want, that the compiler was guessing as a heuristic because I said I want an interface, so of course I'm not going to get copying. And I check constraints. So how do I implement this? So this is the goal I want to achieve with my paper on top of reflection. How can we implement that? Well, I can implement that today. There's the Godbolt link to David's implementation, to the EDG implementation. I can implement it like this. So this is all P2996 and P3940, I think it is. You learn to remember numbers. I don't remember that one yet. I mentioned it earlier. It's the generation proposal that probably will be beyond C++26, but it's implemented both of those. Those are proposals that are in flight and that are progressing. The only thing now that is left for me to propose on top of that is that little syntactic sugar for those first 5 lines, for those basically those first 3 wrapper lines. So, but what's going on here? I am in some prototype namespace writing my normal class. I'm just writing my class widget with the core things I want. But then I am running a const eval function. In const eval block, I'm running this const eval function interface, and I'm passing it a reflection of this widget that I just wrote. What's interface going to do with it? I'll show you on the next slide. But what that does is it says, oh, you want an interface? I will now take this int f, and I will make it public. I will make it pure virtual, because notice class, this would have been private. I will make it public. I will make it pure virtual. I will give you a virtual destructor. I will prevent copying. I'll do all those things. And so this code works. So you can look at the Godbolt there, and you will see that this code works. Now I have class my widget inherits from public widget. Notice it says int f override, and this compiles because the widget f is in fact virtual, because by the time you get down there, it has become virtual. And I can go and use it polymorphically, and everything works correctly. And you can see the output there showing the correct behavior that you would expect. but I got to write not the left-hand side, I got to write the right-hand side. And I'm still proposing that we have this little syntactic sugar, but I can already write this today on that prototype. You can go look at it on Godbolt. And here's what the implementation looks like. I have a const eval function. By the way, const eval, how many of you have used const eval from C++20? Okay, that's a const expr I meant it function. So const expr means it can run at compile time or at runtime. Const eval means, yeah, except const expr, but not the runtime part. It's guaranteed to run at compile time only. That also came from the CPP2 work and from Andrew Sutton and Lock 3's implementation. So thank you, Andrew, Wyatt Childers, and all the folks who worked on that. But here's what I'm doing is I have this const eval function. I'm going to call it interface. It's just a name. It takes a reflection. In the current draft that's currently being spelled, std meta info. These names could change, but that's where we currently are. And then I'm going to ask its identifier name, so I'm going to get widget. The name is going to be widget. And then I'm going to do this funny thing called Q injection. So I'm going to basically now inject this code right here wherever you are in this namespace. So if you go back here, you will see I'm running this const eval block. I'm running it in this const eval block in this location, which is right outside this proto namespace. So in this scope, inject the following, as if the user had written it, as if I had written this by hand. Class, and what's the name? Widget, and there's this incantation. I'm not perfectly, totally happy with the /ID and stuff, but I will take it any day of the week, a little ugliness, if I can get this feature. I am perfectly happy to progress the proposal with a little ugliness this way, because the power is worth the price. So class widget. And here I write public. Notice I'm highlighting all the things that now I am now writing as code. Remember, this is just a const eval function with new extensions where I'm actually writing code saying, now generate this code, public : repeat all the things that you've found so far, or get all the interface functions, add the virtual, this is a function that we're going to see on the next slide, virtual destructor with the same name. I'm going to default the default constructor. I'm going to delete the copy constructor and the copy assignment operator. And that's it. And the fact that I can go and I can then say, oh, and by the way, loop over all the individual functions, I'm just calling another function. This is composable. So I go on the next slide, and here's what those make interface functions do. This is where I loop over all of the members of the type. And if it's not a special member function, then I'm simply going to inject what I read from that prototype into this type that I'm now defining, but I'm going to stick on virtual and equals 0. But otherwise, I'm going to duplicate the return type, the name, the parameter list. I'm just going to stick on virtual and equals 0. That's it. And there's some error reporting, which they don't support yet, but I'm on their case because I also want to have an error message if there's a data member. That's the one part I can do in CPP front today that this proposal can't yet, this implementation can't yet do, but I know they're on the way there. We're on the right path. So that's a complete implementation of that works today in the reflection prototypes for that interface metaclass. The only difference from P707 is that little syntactic sugar. So I've written a few of these in CPP2 syntax in my own experimental compiler that compiles to C++. It's an alternative syntax for C++. And interface is one of them, but there's a whole bunch of others. Regex is the biggest one by far. This one was contributed by Max Sagebaum. And let me just dig into that a bit just to show the kind of thing that's possible when we have reflection and generation. So Hannah, I think I saw Hannah in the room. Are you in the room, Hannah? Wave? I can't see. Yes, she did all her work today. Hannah is the author of the state-of-the-art compile time regular expressions library. This is magic code. It uses const expr and templates to do compile time, have compile time patterns. So you have to know the compile time regex as input. And it parses them at compile time, generates the state machines to do the generation and the compile time and runtime matching. And it's super efficient. If you're curious about how efficient, it's on the left end of this range. And std regex and PHP, pardon me, are on the unfortunate end of the range. But she's done an amazing job showing what's possible achieving these runtime results by doing the work at compile time of building the state machine. So what Max Sagebaum has done, he's actually from not too far from here at University of Dresden, and he has gone and taken in CPP2 syntax with reflection and generation and has built the feature set that's most of the Perl regular expressions. So very similar to what HANA has implemented, and done it using reflection and generation in my CPP front compiler. And so it's two very similar projects. The main difference is that the parsing, instead of using a template stack, uses reflection and code generation. So as an initial experiment, which has now been merged into core CPP front, how do these compare? Well, the code for running the matches is pretty similar. You ask to match the string, you ask to match this particular regex. The main thing is you opt in, and this is the class regex syntax in CPP2. It's just a Python-esque syntax. So it says my regex is a regex type. So this regex meta function reflects over this type, and it goes through and says, oh, look, there's a regular expression. Let me go do thousands of lines of work and generate you a custom state machine just for that regular expression at compile time. So if you look at the sample runtime results between HANA's CTRE and Max's implementation of regex in CPP front, they're pretty similar. They're in the right part of the graph for the runtime results. And these are early results, but that's where you want them to be. For compile time results, this is where we learn some interesting things. So this is using the Haskell regex POSIX test suite. The first bars are the amount of time spent in the CPP front compiler. So for HANA's, there's no bar because hers is pure C++, pure ISO C++, not using CPP front. For Max, there is a bar, but you have to squint. It's more like a line, but there is a CPP front step. The middle set of bars is running in the ordinary C++ compiler. So HANA's in blue and Max's in green. And then the execution time is what is XE? I think that's either link time or execution time. I think that's link time. Anyway, the rest is fast. There is no line. One of the interesting things here is that even though Max is running a whole nother compiler, my CPP front compiler, in front, compilation so far seems to be equivalent or net faster. Now, why is this? One of the things that we should learn is to recognize that doing more work doesn't mean slowing down, because you have to say, what is the net amount of work being done? If I'm doing some work to eliminate more work, I get a speed up. So how many of you have, in the last month, written some function somewhere to cache a computed result so that when the caller calls more than once, you only calculate it the first time and then you just give the cached result? How many of you have done that recently? Well, look at you. You've done more work, so your program should be slower. Well, no. I've done more work because I'm now storing that result, but the program speeds up because I'm saving more work than I did, right? The work I'm saving is more than the little bit of space I'm using to cache the result. The same thing has applied with const expr code. How many of you have already noticed that when you convert it, because I'm assuming we have some people here who like might be inclined occasionally to write a template metaprogramming, who wrote a template metaprogram and then you converted it to const expr code, How many of you have done that and discovered it ran faster as context per code? That's a common thing, a few hands. The reason is, the reason this is surprising to some people is, but wait a minute, context per code, like that's running a whole C++ interpreter inside the C++ compiler. How can that possibly be faster? Well, because you directly expressed your intent. And when you directly express your intent, your tools can love you back. And you said, I want to execute this code. That is faster than indirectly using the template type system that was never designed to do computation to do computation. It is just faster. So it is well known that constexpr is faster than TMP. I expect that we will find that reflection and generation is likewise faster than many things that we do boilerplate by hand, as well as being more accurate and more convenient because we write less boilerplate. So where can this help us? So as I'm looking forward into the future, if we adopt this kind of style for declaratively saying, I'm writing this kind of class, I would love to be able to write, I'm writing a Qt class instead of writing all this boilerplate. I would like to say, to do that, and then have a simpler tool chain, because instead of having to write more information in my source file, either in the same file or a side file, and then run a whole separate compiler to generate stuff and then build them together, I could just have a simpler tool chain and run it in my C++ compiler. That's the idea. In COM at Microsoft, we did this all the time. You would write a COM IDL, or interface definition language style file that was separate from your C++ file because the C++ file didn't have all the information. And so you would do things like add a GUID and write property getters and setters and say, and annotate what things were. And I would like to say, no, hey, no, I'm not writing any class or interface. I'm writing a Windows runtime interface. Oh, that means you want this UUID. That means if I see a property, a member of type property, I can expand it to the getter and setter mechanically. But I could just declaratively say something that's much more natural in C++, saying a property of this type and this type, if I have, say, 2 parameters, has this value. That's simpler code, but it's also a simpler tool chain, because instead of having either an extended C++ compiler, which is the way C++ CX did it, or having a separate IDL compiler like Classic COM did it, both ways are way more complicated tool chains, and I would love to instead just do it in the C++ compiler, and you'll notice at the end still spit out a binary file. So I have put the committee on notice that I will be asking for compile time IO, especially O, especially binary, because of things like this. You can also imagine, I'm sure some of you already are, a compile time text output where you're emitting source code of another language. Like say you're writing a code generator to write Python wrappers or Java wrappers to access your C++ type. That's all the kinds of things you can do, but the point here is in a simpler tool chain, instead of the complicated way we do it outside, we bolt it on today. And finally, here's an example that was brought up by Benedict and Axel. This is, again, back from 2017. They had a YAML script that defined in text form what 5 related classes should look like. And then it goes and generates 5 interrelated classes based on that information, based on that template, and put the right things in the right places. But they had to run it through a YAML script to do it. What they could do with reflection and generation and with P707 syntactic sugar is to say, I'm not just writing any class, I'm writing a pod.io data type. Here are the data contents I want written as ordinary C++ code, which this data type meta function can reflect on and generate those 5 interrelated classes, those same ones I had before, during normal C++ compilation without a separate YAML step. So instead of having the YAML step before and run it this way, just run my C++ compiler. So I gave those examples at CPPCon. You know how comedians will often say, old-style comedians, they'll say, a funny thing happened to me on the way to the... Funny thing actually did happen to me on the way to the elevator in the hotel. So I do the talk. That was on Monday morning. Throughout the day, people would come up and say, hey, nice talk. I could really use that generation stuff or things like that. So that happens. The next morning, I sleep in a little because I'm exhausted. So, okay, I missed the first talks, but I thought, okay, I need to get a coffee. So I leave my hotel room and I start walking down the corridor on whatever, like 10th floor, whatever it was, to the elevators. On the way, I meet someone wearing a CPPCon badge who says, oh, by the way, loved your talk, thank you. You know that generation? Back in our team, we have such a code generator that we would love not to have to maintain. That we have to write ourselves, and we'd love to just do it all in the language. We could use that. As soon as that's available, we would love to try that out. That's great. We got to the elevator, doors open, we went in, doors closed. Partway down, the doors open again. Somebody else gets on. Neither of us know this person. He says, oh, by the way, great talk yesterday. Say, at our team, we have a code generator that generates the C++ code, and we would love not to have to maintain that separate code generator and have a separate build step. Twice between my room and coffee on the main floor. I'm not making this up, and that was representative. How many of you resonate with that? How many of you work in such a team? About, 2/3 of the hands, half, 2/3. This will be game-changing, even in just the simplifying of our language, of our code, but also of our tooling, of our build chains. So welcome to C++'s next decade. We want to build on this. It's going to take us a decade to build it out and to learn all the things we can do with it. But the first phase is now in sight. So we want all information in the source code to be reflectable. That includes things like defaults, because those two functions, we want to be able to, in a metaclass, to say, hey, does it have default accessibility before you wrote public or private? So we want that to be possible. And once we have that, you can imagine that the class and struct we have today are just the two first meta functions built into the language, that each has their own default. It's just default public versus default private. And on the flip side, anything that can be written in the source code, we must be able to generate. It's really important that the programmer is going to want to see what's there and then be able to automate the writing of it so that it's generated instead of being written by hand, but is as if it was written by hand. I noticed that there was a question at the end of Hannah's talk about, so all these great const expr libraries, how do we debug these? And the answer is like, printf. Printf is pretty good. Printf is good, right? That's pretty much where we are right now. Once we start generating code, and I've told IDE owners this, there's a market for it. The carrot is there's a market for them. The stick is your users will hate you if you don't do this in the next 5-10 years. That as we generate source code, in your IDE, you must be able to do things such as visualize it, say click to expand to show like the source code you wrote with the metaclass name, or expand to show what's actually generated so you can say step into and debug that code. I've put them on notice, and you all hold them to account. You put your vendors on notice as these things become available. And as const expr is already available, give us compile time debugging tools. With reflection, we're going to need them even more because we'll always have to see what we generated. And of course, the text and binary output that I mentioned. So as long as we have that North Star of use cases guiding us, we'll do well. We want to avoid bottom-up design piecemeal. See more details with a mini panel in my CPPCon version of this talk where Andre came on stage and we talked about that for a few minutes. So he had some interesting observations about things he would have liked to have done differently in D, but time and resource constraints are valid. So finally, safety. Remember that programming language safety, it helps both the others, software security, software safety, but it also makes our code higher quality. It just reduces errors in our code. So even if we weren't talking about memory safety and NSA and foreign threat actors and all those things, memory safety is good just because we write fewer bugs. Even if nobody's exploiting them, writing fewer bugs, that's good. Like, that's a big thing. So consider initialization. So would Bill and Ted, would they say this is righteous, most excellent code? Notice line A, today is not initialized, remember. I know we think it's stray, but it's not initialized. And then we call a function to fill it. How many of you say, yeah, if somebody wrote that and I was reviewing it, I would allow that code to be checked in today? I want to see more hands, because this is what you do today. Okay, yes, all right. You're going to make up for it by voting twice, Jens, I saw. So this is valid. This is what we write today, because we can't do better. I mean, if you reject this on code review because of the uninitialized variable, this program is actually ideal, because you don't have dead rights. You don't have fake rights, dummy rights to the contents of A that are only going to be overwritten by Phil. But yeah, what's the problem, right? How do you know that Phil will actually fill up all the elements of array? You have to know that. And that's the problem. Static analyzers, humans, have a hard time proving or knowing that fill of A will do that unless they go and look at the source code, right? Unless fill happens to be spelled memcopy or something like that. You know, we know a few of the popular words, but in general, we don't know without going into the source code, which static analyzers hate to do because it's not scalable. You want local analysis, not deep analysis. But if we said, oh no, that's going to be initialized from now on, the problem is we know the dummy rights aren't needed, but the optimizers are terrible at removing them. And I have seen people, I've sometimes been that person, back before I knew better, who said to the optimizer, well, it's a dummy right. Can't you just see that and not do the right? You're writing to it, calling a function, and writing to the same location again. Long story short, it's hard for the optimizers to see those semantics for the same reason it's hard for humans to, in the first case, to see those semantics. For the same reason, they can't prove that fill of A fills A. What if fill is separately compiled and you're not doing link time optimization? It turns out this is very hard to eliminate those dummy rights. So that first code up there actually is pretty ideal today. The problem is it's fragile, and we can't do better right now. What we really want, we can do better by jamming in indeterminate values. We talked about that in part one of the talk. That is an improvement, but it's not the ideal. The ideal is what we really want, initialize before use. So C# and Ada have this, where you have a local variable. You don't have to initialize it right away, but you have to initialize it later in the function before you read from it. You must initialize it. And it turns out that's actually a really usable rule. I have implemented that in my compiler in CPP front, in the CPP2 syntax, which means, and I do this for every type. It's not just for ints and for arrays. It's for every type. If you declare a local variable without an initializer, it allocates space but does not run any constructor, and it knows it's uninitialized. It guarantees that it's initialized before use on every branch path, and you can also initialize by calling a function that has an out parameter, so we know that it's writing to it, and that's composable. And we can do that with local analysis on the caller and the callee, and so we can compose and do this. So for example, and this is using my alternate syntax just for illustration, this so you can see how it works. If I declare A is an int, but there's no equals something, then if line 2 were not commented out, it would be a compile time error. No, this is an error. You can't use A before you initialize it. But then you initialize it, and now you can use it. So this is done. I've demoed this a couple of years ago at CPPCon in the original CPP front talk. But this is true for any type. It can be a vector of strings. And as long as I go and I initialize it before use, I'm OK. So same rule for all types. I don't have to distinguish between little ints and big arrays on the stack. They all follow the same efficient, safe rules because you get safety and efficiency. A couple of screenshots that I showed back then. If you initialize P as a pointer to std string, this is again using my alternate CPP2 syntax. If something, I initialize it, but now I haven't initialized it on both branches, so you'll get an error message that says so. Local variable P, you tried to use it on that last line, but you didn't initialize it on the implicit else branch. You have to initialize it on all the branches, and you get this error at compile time. And similarly, you can go and call a fill function that declares an out parameter. That's the only extension needed so that we know that, yes, this actually will call a constructor. This call at the bottom inside the fill function, if fill is past an object that has not been constructed yet, that resolves to a constructor call, not an assignment call. It's smart enough to know which one to do. That's just to show that initialization safety that's efficient is really possible. So I'll be proposing that in the future, in the next couple of meetings for C++ itself. Another thing that I've already implemented and that I want to propose to C++ itself, and we're going to start having this conversation next week in Poland, is say that at the call site, every subscript operation of the form A sub B is bounds checked automatically at the call site if you can say std size of A and B is an integral type. So this works for contiguous ranges, it works for views, it works for std span, std vector. It also works for Qt containers that are contiguous and that provide std span. So one of the nice things that I really enjoy about this is that my results so far, because I implemented it at the call site, when I write CPP2 code by default, I get full bounds checking for every STL container, including the non-standard STL compatible containers like Qts, for every array, for all the ranges and views, the support size. And I didn't have to upgrade my standard library. This works with GCC standard library, with Clangs, with Microsoft's. It works with non-standard libraries like Qts, and it works for C arrays. I'm loving it so far, and I intend to propose that as something that is either on by default always, or at least is on by default in a bound safety profile, so that in the future, and say maybe in C++29, this is something that will be easy to adopt in large parts of code. And one thing I really like about this proposal and about this approach is if I do the bounds checking inside each subscript operator, A, that's more work. And B, I got to go convince every library writer to go upgrade every type subscript. So like if they add a precondition, I have to make them go do that. I have to then get the new library, wait till I get a new library from each person. With this approach instead, I can take all the existing code, just recompile it with that feature enabled, with call site bounds checks enabled, and it just works with all that existing code. And that, again, is that holy grail of adoptability that I really hope that we can pursue. So here's an example. If I have an int array or a std vector of int A, it doesn't matter which definition of A we use, and then we go and we print A sub 1, A sub 2, A sub 3. Do you see the bug? It's an off by one bug, right? I wrote this bug, and here's what I got. On Visual C++, bound safety violation, out of bounds access attempted. I attempted access at index 3. The min-max range is actually 0 and 2. And I got the same error when I compiled with GCC. This is one of the advantages of doing it at the call site. It's really cheap to implement, and it just starts working, lighting up everywhere. So these are screenshots that work today, and it caught a bug that I wrote in my test code. So we have to prove the rules really work. We have to prove that when we come up with a safety proposal, it's not just an ivory tower design, but it's something adoptable. And a really, really important litmus test, I think, is how close can we get? We're not going to always get there, but how close can we get to, I just take my existing code, I recompile it with a new compiler, and it's safer. Now, we've already done that with UB in C++26. Take your existing code, compile it in C++26 mode when the 2024 additions are implemented. It will just be safer because uninitialized locals will no longer be UB. Add subscript checking. Just recompile your existing code, it'll be safer. Now, some things absolutely will require code changes. Some code is just structurally unsafe and wrong and will not be safe automatically unless you rewrite it. I've never said otherwise. You will have to rewrite your code in some cases to get 100% of the safety benefits. But those are examples of things where if we're intentional about it, we can deliver maybe not 100% of the safety benefits, but some fraction, 20%, 80%, just with a recompile, without manual code changes. And I think that is a worthy thing to aim for, to see just how far can we turn that knob. How much of the safety benefit, not 100%, but how much of it can we deliver to existing code without code changes? So we want to add features to let the programmer express their intent. We want to enable compilers to take advantage of the intent that's already in the code, like that we know the bounds of STL containers and can use them, and let them write what they want to do, not the mechanical details of how to do it. So that's a path where I think that reflection and safety will lead to further simplicity. And as we target safety parity with other languages, and as we pursue reflection as a generational improvement in C++ that's going to just light up our next decade, much the way C++11 lit up a new decade for C++, I think we're going to do it again. And it'll be a fun thing to see. So it's late, but a few of you have already had beers, so you are at least one ahead of me. And I'm happy to take questions for a few minutes as long as people are willing to stick around. So how would you like to do the questions, Jens? There's a microphone. Please come up to the microphone. Who will be first? Step right up.
So, do you have any questions? Please come to the microphone.
I wouldn't blame you if at this time on a Friday night you decided your question was, where's the bar?
Hi. I think my question is a big one, maybe, but it's very interesting to me. So I have seen another programming language that also introduced reflection, but they did it a little bit more generalized, as you or the committee proposed it apparently for C++. And I was wondering what you think about that. So the way this language that I'm speaking about did it is they just say, we are running everything that generates codes within our own in the same language, meaning we just have a special character that we put in front of the code that we want to run in the first iteration of a compile step in that language. That outputs just a string, and that string just gets injected into the original source file. And that, to me, seems like a super, super general approach that would work with basically everything, not introduce another complication in the language, really just use the existing leverage to generate code within the language in an iterative compile step. Kind of like you do with CPP2, if you will. And I really like that approach, and I was wondering, wouldn't that be better than what I've seen here today?
So, that's an excellent question. So like Sean's circle compiler is a similar kind of step. I'm not too familiar with Zig, but that's reminding me of Zig. So correct me if I'm wrong, but I think Zig, no? Okay.
I'm talking about another language called Jive from Jonathan Blow.
Ah, yes, Jonathan Blow's language, that's right. First of all, I think the extra character, there's a lot of similarity to the const_expr block that you saw to actually just, here's a const_expr block here, run this code, because that has to be run first. Think about where it's being run. it's being run in the C++ interpreter that's built into the C++ compiler. So it's being run before the rest of the compiler runs. So you really do have those two steps. So I think that any approach like this that does it at compile time, I mean, I'm excluding things like C# and Java that are all runtime based, right? But any approach that does this at compile time, if it's going to be sane, will need to have a couple of phases like that. We'll need to have generation and then the rest of the language. Now, you may interleave those because, like, for instance, in CPP2, as I'm parsing, I let you say, okay, I've defined 100 types already. Now I'm defining the 101st. I parse it. Oh, there's a meta function. I run the meta function, generate the code on the fly right then, but I'm stepping back into that mode, or I'm generating the code, and then I finish doing the semantic analysis and everything for it. So it's pipelined, but it's as if I did everything first and then everything second. It's just interleaved and pipelined. But I think you will find those two phases in general. Now, one of the things that maybe you're thinking of too is the ugly syntax. Yeah. That doesn't affect the phases, but I get you. I hear you, brother. But I want the feature so bad. I'm happy to try to put lipstick on it afterwards. I don't know what the right metaphor is. Paint on the wall. I'll buy the house. I can paint it later, the right color. But I so want the feature because it's going to liberate the kind of programming that we need to do.
Yeah. You know that if we do it though, then we're probably going to be stuck with it forever, like with most things in C++. So let's hope it works out like you think it is.
And that's a fair comment. Having said that, we do over time manage to improve things by adding syntactic sugar for patterns that we see people using. So I do expect, as reflection continues to evolve, and as we see the patterns people use, that it will get richer and the code will get simpler just because we'll be able to more directly express the patterns that as they emerge, as we see people use them, that we can give first-class support, just like we did with range 4 and other examples like that. But those are very valid comments.
I would like to talk with you about that a little bit more later, but first, another person.
Okay, thank you for giving us more insights on that. And for the initialization tracking, do you also do partial initialization tracking? So if we have an array and we initialize the first element, can we access that? Or is that not part of your proposal?
I currently do per whole object. So if it's an array, it's either uninitialized or it's initialized. And I do not currently, actually, I have to check whether, maybe I do. I can't remember if I added this yet. I do not check to make sure that you wrote to all elements of the array. It's just, there at least some initialization happened in the array. It's up to you you've initialized as much as you're going to initialize, but you know you're constructing it. And so you get the hook to do the initialization you need to do. So you know initialization was done. But I don't think I verify that you wrote to every single location or to every data member of an object or something like that.
But wouldn't that be beneficial to do?
Well, it could be, but so there's two cases that are similar. So when you think of a big object, the two simple cases are it's an array, so it's n of the same type, so like 100 ints, like an array of 100 ints, or it's a class with int a semicolon, int b semicolon, etc. It's like, or int a was 0, a 100 up to a100 or a99, right? Certainly for the class, we expect the constructor to initialize everything. In fact, it's required to, it's enforced, right? So that case is already covered. When we initialize the array, so notionally what we're doing is we're saying you're writing as if the constructor of that array do something sensible. And so we could special case for arrays, hey, like check to make sure that you wrote to each buffer, but it's a special case thing. The general case where it's a big object and a type is already covered by the constructor rules. But yes, arrays, we could do that, but it would be for only array cases, which is a common but narrow case. Does that make sense?
Yeah, I see.
Yeah.
Thanks.
Thank you for your talk. the question that I have in mind is maybe it's a bit of a personal question regarding CPP2. So a couple of years back, I saw your talk at CPPCon about can C++ be 10 times more simpler. So regarding that, is CPP2 something which is often being talked about in the standard committee meetings, and is it something which can be brought to the users of C++ as a whole, or is it going to be provided to the main standard C++, ISO C++ as bits of syntactic sugar in a gradual way?
This is a good question. So it's my personal experiment to try out some ideas, to learn things. And most of the key simplifications and power features I am already bringing as proposals. So I have a pattern matching inspect proposal that's partly implemented in CPP2, metaclasses, of course, and things like that, which do not depend on the syntax for their power. So when you look at the 10x simpler and safer goal of CPP2, most of that doesn't rely on syntax. Like to get all the way there, yes, you need a context-free parse, order independent grammar, like things like that. But most of it, it turns out, come from, well, actually from a few things. Two things are the big ones: meta functions, reflection and generation, and parameter passing. That's like half of the simplifications come from those two things. And those two things are easy to also propose individually, which also lets you decouple them and try them out and test to make sure they carry their weight, that they have the correct cost benefit. So I'm glad to see that reflection is well along the way. That's been a journey. Some of us have been pushing on that for 10 years. David has been pushing on it for 21 years now, I think. So it's a long arc, but I think that will be really good. But it's my personal experiment, and it's designed to feed proposals into ISO C++ to make ISO C++ better. As for the syntax itself, we'll see. Like maybe someday I might propose that too, but it's not on my radar right now. But I do want to take what I learn and propose it. And then, of course, that's just one person's opinion. I'm just one of hundreds of people. Like literally, nobody gets more voice than others. Everybody gets one vote. And to get anything done, you have to actually provide a technically convincing argument, not just hand-waving and a light show. You need to actually do the hard work to show something works and convince people, and then you've got a shot at getting it in the standard. And that takes a long time. It can take many, many years. The payoff is that when you succeed, and you may only succeed like 1 out of 10 times, but when you succeed, you've made the world better for 10 million programmers. And that's a pretty cool thing to be able to do. And the same thing when you ship your software, you're just like, okay, I've worked on this hard, but now all my customers are going to be this much better off because of what I did. That's the payoff.
Yeah, cool. Thank you so much.
Yeah.
Well, there's a few online questions, and I'd like to ask you first. Stefano Kayasa, I guess, asks, you mentioned a lot of potential safety improvements, and even the low-hanging fruits seem they may be available maybe with C++ 29.
Oh, sure. Yeah.
With that, will that be early enough to be able to fulfill the new requirements from regulatory agencies?
I think yes. So first of all, if we're talking about the ones that hit the news in the last month or two, that means you have to have a roadmap for what your plan is by some date, like 2 years from now. I forget the exact date, something like that. A roadmap can be adopt C++ 26 compiler and recompile in that mode so you have no uninitialized local variables. Adopt the safety profiles that we'll be standardizing. So that's the kind of thing that a roadmap can include. The other part of that is that, yes, not all the things we're working on will make C++ 26, but some significant ones already have. Even there, you can use some of those things today. I showed code where you get those uninitialized variable benefits today with compiler switches that all 3 major compilers already implement, so you don't have to wait for C++ 26. You can recompile your code today with no UB from uninitialized locals if you're using Clang, GCC, or MSVC, just using those switches I showed you. You can do that now. You can go home now and do that. If you're remoting in from your hotel rooms, you can get a beer, go to your room tonight, and then do it. Don't check it in until the beer's worn off. But so, and even things that are in C++ 26, 26, how many of you think that C++ 26, because that means the year 2026, how many of you think that sounds like kind of far away? Come on, be honest. Oh, wow, forest of hands, okay. So they're with you, Jens. Clang and GCC have already implemented 2/3 of C++ 26, guys. Clang and GCC have already implemented 2/3 of what's in C++ 26 language extensions. Compiler vendors, now that we're shipping reliably every 3 years, it's not like C++ OX when people wondered, are they ever going to ship again? How many times is this going to change? Because we're now in a regular cadence of shipping, compiler vendors say, that's reliable. I can build product schedules around that. And they are aggressively tracking the standard. So it used to be with C++ 98, it was 5 years before the first conforming compiler, fully conforming compiler showed up. And yeah, that was partly because export, but still, it's also partly because of not all compilers valued conformance right away. But that has so much changed. We are now in a world where it is normal to see at least one of the major compilers implement the whole thing the same year as the standard, and most of it even before the standard's ink dries. So many of the things I'm talking about, the reflection isn't implemented yet in the major compilers. One of them is a Clang fork. But most of what's in C++ 26 has already been implemented in GCC and Clang trunk. So think of C++ 26 as near term. I mean, the feature freeze for C++ 26 is only 7 months, 8 months away. It's coming on like a freight train. It's coming faster than you think.
All right, so I may give you some honest feedback.
Please.
So we happen to have someone here who works on those roadmaps you mentioned for one of our big companies, and he's a keynote speaker too, and he will be around tomorrow. I would like to ask you to talk to Titus Winters, because we did an interview, and he mentioned that he is on basically the team doing the roadmap for company he works for. So please talk to him.
Yes.
And the next question is like basically also kind of hitting this again. And it's like something really the community cares about. So I heard earlier that at the conference that C++ developers basically have 5 to 10 years to look around and prepare for whatever comes next. How do you think C++ will meet the industry needs requirements in the next 10 plus years? When do you think CPP front will be production ready for large industrial projects, etc.?
So that's a complex question. Let me tease it apart. So the CPP front is easier. It's not intended to be a production compiler. It's a personal experiment. Having said that, I recently, was it a month ago? It's time warp. I don't know if it was a week ago or 2 months ago. I put a permissive license on it, so now it's Apache 2 LLVM. So it can be used for commercial use, but you'll still find bugs and incomplete features, and I'm still adding to it. That's not my main goal. I want to learn from it, and maybe it will become something like that someday. But my main goal is to contribute to ISO C++ features that will go into the mainstream compilers. And now the early part of your question, oh yeah, the roadmap, 5, 10 years from now. You can see very well what is coming down the pike with C++. In talks like this, I've summarized what you can see the proposals that have been worked on for a decade, and now they're landing. And we can see what's coming. The writing is on the wall. Reflection and generation are going to dominate the next decade. They're going to be a game changer. The writing is on the wall. We are serious about removing undefined behavior, large swaths of it, and there's a paper in the mailing for next week by me to remove all of it by default with ways to opt out. So we're taking those things seriously, and everyone can see them coming. One thing about the 5 to 10 years, though, that I'll mention, and this isn't the 5 to 10 years you mentioned, but it's a different 5 to 10 years. Sometimes I hear, yeah, it's great to hear about C++ 23 and C++ 26. I'm still arguing with my boss on turning on C++ 20. How many of you felt that? Yeah, right. And compiler vendors, they have telemetry. not the creepy kind, the useful kind and the responsible kind that say, we can see only X% of our customers have turned on C++20, right? Do not make the mistake of thinking that that is the same for every release, that it's just always like a 5-year lag, because it's typically a 5-ish year lag between we ship a standard and it gets broad market adoption, broad market penetration, like where most projects have turned it on, right? I like the features, don't get me wrong, I like the features in C++ 14, 17, 20, 23. But concepts is great, but people are not beating down the doors for it. Coroutines are great. They're not something that 90% of people are beating down the doors for. C++ 11 was the most impactful release we've ever made because everybody and their kid's sibling wanted range 4 and lambdas and auto-type deduction and smart pointers in the standard, finally, and all of these things. These are broadly useful features that everyone could use. Concepts are great, but they're for a narrow use. Coroutines are great. They're still a fairly narrow use. So it is not surprising to me that adoption has been, we'll adopt when we get to it. We want the latest standard, but it's not one of our top 5 priorities because we have other customer issues and things like that. Do not expect that to be the same for reflection. How many of you, more than half of you, put up your hands with, yeah, I have a code generator at home on my team right now that I could replace with reflection? I expect you to be knocking down your compiler vendor's doors the moment that the reflection is standardized and say, where is it? Give it to me now, and you will want it now. So I actually expect, as soon as we start shipping, especially reflection, but also the safety improvements, I expect to see much faster adoption of standards than we have over the last few, simply because it's a much more compelling feature that people will feel more urgency to adopt. That's my expectation anyway.
Okay. So hello, thank you for your talk. You mentioned at some point about initialized variables in defined behavior, and I was curious if you have any plans for invalid memory accesses or how to determine at compile time if there is an invalid memory access or some security problems like buffer overflows.
Yeah, that's an excellent question. So of those 4 safety buckets, bound safety type, memory, initialization, and lifetime, bound safety, like you were just talking about, is the low-hanging fruit. It is the one that's the largest of those 4 in terms of number of vulnerabilities that are actually being exploited. Buffer overruns and underruns, so like read and write, that whole matrix. And it's the one we can do the most about. It's the low-hanging fruit we can do something about much easier. So with subscript checking, like I described in this talk and that CPP front already does, we can eliminate safety for subscripts for contiguous containers. So that goes away. Now you still have to, we'll take your code that does pointer arithmetic and change that to use span and then use subscripts checking on span. The bounds checking does not yet support iterators. So I check subscripts, but I don't check iterators. But all of the vendors have iterator bounds checked modes you can use. Some are more efficient than others. Those that are less efficient, I happen to know, are going back and looking at how to be more efficient because everybody wants that checking. So it is definitely one of the things that we need to look at, but I think that one of the ones we'll get to sooner is the out-of-bounds access and being bound safe, because I think it's the most important and the easiest of those 4.
And how much does it add to latency?
Oh, how much does that add to latency? Mm-hmm. You mean in terms of the checks bounds checks that you do? So I think what you're asking is how do we deal with bounds checking overhead? Okay, that is an excellent question. So speaking of what I know of the Microsoft backends, because I spent quite a lot of time there in that team, I know that, and this is not a complete answer, but I know that there's a lot of bounds checking that was done in the backend for managed code that is just directly applicable to C++ code. That doesn't cover the whole thing, but it's already like, hey, there's a lot of commonality there. We do know we do know there's two other buckets of things we need to worry about. One is C++ abstractions, making sure that making them safe is efficient, specifically bounds checks for span. We need to optimize span more to make it pass in registers, so that people don't have a reason to use a pointer in a length. To hoist the bounds checks better. Those are things that compilers aren't as good at. So I'm happy to point out the places where we still need to improve. So we need to optimize those bounds checks and hoisting them. That's going to be where opting out is important, where you need to tactically opt out. Hey, I'm in this loop. The compiler can't see that it's bound safe. I already did the check up here. I'm just going to opt out of, suppress the bounds check here inside my loop. Trust me, because I'll take responsibility, because I know I checked it up there. So opt out is important. But also, that's the third bucket I was going to talk about, was the more we provide features that are safe by construction, then no checking needs to be done. And one example of that is range 4. So if you do a range 4 over a span, you should only get one bounds check. Now, current implementations probably don't do that yet, but that is low-hanging fruit for them, because the range 4 by construction cannot access elements outside the span. So all you need to do is prove that the span doesn't change while you're iterating over it, right? So that the bounds change. But then you can hoist the bounds check and just do it once. So there's the more we can do that, correct by construction, no runtime checks required. So does that kind of give you a flavor for the ways to deal with it?
Yeah, thank you so much.
Yeah, you're welcome.
Perfect. Thank you very much. Thank you for the talk. And I have a question regarding code generation. Could you jump to the 45th slide, I think?
I love it when people remember slide numbers.
It's the one with the interface.
Sorry, that just sounded so Seinfeld to me. The one with the interface.
Yeah, okay.
This one? This is slide 45?
Right. And there's the make interface function. And if I understood it correctly, like you got the prototype of a class or an interface, and you use all the functions and make virtual functions out of it, or abstract functions in that case.
Yeah.
And the original function, the original class, will it stay there and be unused? Because it's like a class with only private members, and it is in a proto namespace, so it's just a duplicate class.
So here we are. And I broke this into two functions because it wouldn't fit on one slide. So here's the inner loop of, for every class or for every function in the prototype, generate this function with the same name and signature, but make it virtual, pure virtual, equals 0. Stepping one back from that, that's in the context of generate this class, so you get a prototype input. Now I'm generating a new class in the current namespace, where I'm being invoked from, that does all that takes the functions in that prototype, but also adds destructor and suppresses copying and all those things. It generates the entire class. So what happens here in this code is, right now, the way that I have to write it using the prototypes of the current P2996 reflection and I think it's 3294 generation that's built on it, is I have to basically write the class off to the side somewhere. So I just stick it in a proto namespace. And then I read that and treat it as my input to the interface function, saying, okay, now here where I'm invoking you, which is outside the proto namespace, here where I'm invoking you, peek into this thing I'm giving you here, and now generate it with these rules, right? And so your question is, yeah, but does this mean that this proto widget is still hanging around? Yeah, and nobody's going to use it unless you explicitly say under proto use it. But this is one of the reasons I want to propose, and I say this in the paper, one of the reasons I want to propose that sugar, because when you declare your intent, you know where this is going? When you declare your intent, hey, I'm only writing this body for the purpose of generating this type. The implementation could still generate a prototype and then do it. It could still be the same implementation. In fact, it is in this example. But then it would know it could throw it away, right? Because you've declared your intent, and then compilation can be more efficient because you're not keeping around as much of your AST. So that's really good. You notice that subtlety. Most people don't say, but tell me, what happens to the prototype that you wrote? Does that just linger around? So good eye.
That means there's also an impact on the memory. That's what I was thinking.
Yeah, and then getting rid of it also means it's there temporarily as you're building the thing, and then you throw it away, so it's not consuming space. It doesn't add to other data structures that are keeping track and pointers into the AST and stuff like that.
Thank you so much.
You're welcome. Thank you. One more and then a beer. You all are very persistent. Thank you for staying so late.
Well, we can make that happen. So here's a question about reflection I think is nice. What are the reflection features that are not likely to make it into C++26, which you will miss the most?
Oh, that I will miss the most. Generation.
All right?
Yes. Oh, wow. You're right. I should stop with a short answer. It is possible to give a short answer.
Anything to add? Anything to add?
Okay, and the metaclass syntax. But that's part of generation. Such a troll.
So I wonder if they could reuse the curly brackets construct used by the std format strings to make it more unified and what is known to be parsable at compile time.
We are going to be spending, I think it's a day and a half next week, talking about reflection syntax. So the answer to, could it be nicer with a certain alternative syntax is yes, very likely. But even with those \ID and \type name and those kinds of things that I called out and made gentle fun of, that is close enough. It is not what I would have designed. If you want to know what I would have designed, look at CPP2, and there's almost no decoration, it's just strings. But I will take it. If I can get that in a production C++ compiler and write code against it, I am at one happy camper.
That just was my question.
Is that beer for me?
Maybe. It's, just let's wrap up the evening. Thank you, Herb.
All right. Thank you very much for coming. Enjoy the rest of the conference. Thank you.